Hello. Today, I will present a new federated learning framework for Internet of Things. You can see that a machine learning framework for Internet of Things, and we will try to evaluate this framework on a real use case coming from the application or coming from an Internet of Things application. So, Carl Berger-Devroux, it's a French company. It's the leader of maintenance management system, and it's provide a new solution for maintenance for the clients, and they try to add new services for their clients. And one of the services is predictive maintenance. Why? Because predictive maintenance try to anticipate and predict the failures in order to avoid some chaotic breakdown and in order to schedule and planify maintenance actions correctly. Before that, we have a chaotic shutdown or a chaotic breakdown of mini equipments. And also, using predictive maintenance, we can reduce many things, especially the downtime, the cost of maintenance, because we can plan correctly the actions in the best time and with the optimized manner. Also, we can decrease the breakdowns and we can also eliminate it, but we can increase, for example, the investment and the production, because we can estimate the lifetime of our equipment or when we have to plan the maintenance. This is from a point of view of a client, what the client will earn from using predictive maintenance and predictive maintenance models. But for the company, and thanks to the new technologies, the predictive maintenance is a new market of maintenance, and a new market that it's grow each day, because we use new solution like Internet of Things, cloud computing, machine learning, and data analysis. And when we talk about Internet of Things, the company will provide an installation, a total deployment of connected objects in a sensor network, and also sending this data to the cloud computing in order to store this information or this data, and providing computing resources for machine learning models, train machine learning models for deep learning or traditional machine learning, and also data analysis in order to provide a gut view of different equipment using, for example, a real-time dashboard and real-time monitoring. But using Internet of Things we face using this technology of Internet of Things with the sensor network, we face many problems. The first problem is that data transferring is too costly, because when we have to send the data, we will use cellular, for example, we have to pay for 4G or 3G. And also, many data are too sensitive. For example, in many cases, we have to build a model of predictive maintenance for healthcare equipment. And in this case, we cannot use the data. We have to keep the data locally for the hospitals, and we cannot build predictive maintenance. And this creates another problem for building a good approach for predictive maintenance, and a big limitation using the Internet of Things and the data-driven approaches. The second problem, if we try to build local model, we will face two problems. The first problem is about the quality of the data. That means that if the data is sufficient or representative to build a good model of predictive maintenance, because when we talk about Internet of Things, we talk about an important element, that is the context awareness. And each equipment plus the context, we have different anomalies. And in this case, if we build a model, will be a biased model, because we don't have different possible anomalies for this type of equipment. And also, the most important thing is to study the life cycle of our equipment. Also, in many cases, we have the data, but it's a small data. It's not enough to train the model and to build a machine learning model. And we have a lot of problems, like an underfitting model, that we cannot use it to predict or to detect anomalies in the equipment. But the third problem is the various devices. Like I said, that when we have equipment, distributed equipment with a geographic distributed, we have a different context and we have a different use. So in this case, we have a statistical behavior will be different. So in this case, we have a data that it's not identical distributed. And we cannot build a good model based in using a statistical behavior or heterogeneous statistical behavior. And if we have enough data and we need to build a model of each equipment, for example, you have to imagine that we have thousands, hundreds, or thousands of models. In this case, we will have a number of models that will increase with the number of equipment. And we will have a big problem that is the management problem and orchestration problem, because we have to update these models, we have to deploy this model, and it will be complicated. So from this problem, we start thinking about federated learning as a solution, because in federated learning, the first problem is the sensitive problems, because we have to keep the privacy of different clients, of different participants, of user. Also, with the federated learning, we can share the information without sharing the data. And in this case, we can solve the problem of sending the data or data transfer, and also the quality and the quantity data. And with federated learning, we try to build the model without by using a new technology, a new method or approach to bypass the statistical behavior heterogeneity. And from that, we start working in federated learning. So what is federated learning? Federated learning is just a collaborative, it's a new approach proposed by Facebook, by Google in 2017, in order to build a collaborative, in order to build one global model for distributed participants. And that will be that multiple participants will build collaboratively one and unique global model that will be used by the other participants. So for each round, we define in federated learning what we name federated learning round. It's an ensemble of steps. The first steps is to define what type of federated learning or what type of task we have to learn, we have to execute. And we have two big types of tasks. The first one is to evaluate the global model if we already trained the model. And the second one is to train the global model. So we have to choose which type of federated learning task we'll have to learn, we'll have to train, to execute. Sorry. So if we like we see in this figure, we have the first step is the participant selection. For example, here we have two use cases. The first one is for mobile phone, and the other one for hospitals. So before starting training a global model, we have to select a set of participants that will be used to represent the other participants. So in this part, we will select, for example, based on some criterion. For example, a mobile phone, we can use connectivity, resources, if it's the battery or other information that help us to build correctly to finish correctly this round. The second step is to initialize the model, the global model, if we don't have already trained the model, and send the model for different participants. In this case, we focus on the mobile phone use case. And each mobile phone will train these models locally using their data. For example, in the case of mobile phone, Google has already prepared the environment with Android, with a lightweight database that collects the data and some process that will execute correctly this process. So once this model is trained, it will be sent to the server in order to aggregate these different participants, the different model in one and unique model. This is the global model. Once the global model is created, we can run another federated learning around. We start by selecting a new participant and local training and aggregation until our model converge. And by the end, we can evaluate it as a federated learning task. But if we change, for example, if we replace, for example, the mobile phones or the hospitals with with the servers that we have in this environment with a connected object. When I say connected objects, it's an object where we will install, we will deploy a set of sensors. So with connected object, so the first problem that we will have is the communication, because we cannot run directly a communication between the connected object and the server for 1,000 or 100 rounds, because we don't have enough connectivity, we don't have enough energy, and we don't have enough resources to run that. This is the first problem to execute federated learning with this generic approach, or this client server approach. This is the first problem that we faced to use federated learning in an industrial Internet of Things. So like I said, this is the first problem, because we don't have resources, we don't have enough communication, we don't have energy to train these models. But the second problem is, like, it's coming from the resources problem, because resources problem, it's very hard to train a neural network, for example, in a connected object. Because yes, we have tiny ML approaches, we have, for example, quantization, compression. All this is solution after training models. It's not before training models. So in this case, we can't train a neural network model in a connected object. And also, the scientific contribution focus in how to aggregate neural networks, and we don't have enough solution or enough contribution for the aggregation of traditional machine learning that we can use in limited resources objects. And like I said, also all these studies, because federated learning has explored in many use cases for IoT also, but the different contribution was on a generic architecture when we talk about edge and communication between the edge and the server, but we didn't define how this communication will be and how we can execute this communication. So we will try to define in a standardized and Internet of Things architecture how to use federated learning. So what is Internet of Things? So Internet of Things is just an extension of Internet. The moment or the time when everything starts sending the data over the Internet, we start talking about Internet of Things. And the things can be a car, can be a room, can be a home, can be everything. And at this moment, we start talking about Internet of Things. In Internet of Things, we have many architectures. We have, for example, the 3-layer architecture, 4-layer architecture, 5-layer architecture. But in this work, we will try to use the 3-layer architecture because it's the fundamental one, and the other architecture is just the extension of this architecture. So the architecture, the 3-layer architecture is just, it starts with the devices layer. And in this layer, we have the objects where we install for example, the sensor and the actuator. This object try to collect the data, just collecting the data or aggregate this data. The second one, this data will be sent to a gateway or a node IoT. For example, in this case, we have, when we talk about node IoT, can be a gateway or a middleware, Internet of Things middleware, or a Internet of Things server. In this case, all the data collected will be sent to this gateway. The next step is to send the data over the network using these gateways. We will send the data using Internet of Things networks, or we will use the common protocols like MQTT, or we can use HTTP protocols or 3G protocols. Finally, we have the application layer, and this is the layer where we can implement our logic, and we use in general what we name Internet of Things platforms. And in this Internet of Things platforms, we have the interfaces that communicate over the network. We have the storage, and we have the data processing, and finally the monitoring and the dashboards. And in this case, this is the part that clients in general or people use to manage all these interfaces, all this environment, Internet of Things environments. This is the ETSI standardized architecture, European Telecommunication Standardized Institute standardized 3-layer architecture. But if we can see that we didn't consider like security or other other aspects here, we can add other layers, for example, a middleware layers or security layers or other layers in this context to build a good, to build, for example, to take into consideration the other aspects. So next point, the second point, it's what is edge in this case? The edge in this case, it's the last point in the sensor networks. And we can say that the edge in Internet of Things it's the gateway. In this case, if we can define it's all the data before the gateway, it's the edge. And after the gateway, we start talking about the cloud. So if we want to implement federated learning in Internet of Things, we have to start thinking where we can offload this the different learning approach at this level of the gateway level. So from that, we start working on the architecture or updating the architecture, defining new sublayers or new component to manage all this information. The first one is to define the new sublayers. Data generator has the same traditional rule as devices that just collecting this data. The second sublayer is the new sublayer that we are defining is the local orchestrator sublayer. And in this layer, we have data preparation. So it's directly connected with different objects in order to data prepare, data storing, and also local training orchestration. So a new component that we will add at the gateway level will help us to prepare the data, to evaluate the model, and also to orchestrate the training of the model for each component separately. And in this case, we can manage the data of each component or of each equipment in the Internet of Things environment. And also the important thing is the monitoring. So we have to monitor the models, we have to monitor the resources. So we add the new agent to monitor all this environment. And the third level or sublayer that we add is the global orchestrator sublayer. In this case, we have a global orchestrator that manages the local orchestrators and then help us to deploy on demand all different local orchestrators, prepare the environment for the local orchestrator at the gateway level, and also manage the training for federated learning, manage aggregation for federated learning, the training orchestrator, and also the monitoring of executed models. So we have to monitor this at this level and at this level also in order to have the God view of this architecture and manage correctly the full architectures. So to take a quick deep view or a close view about the global orchestrator. So in this global orchestrator, we define two types of interface communication. The first one is the management interface. In this case, we will help us to manage the local orchestrator, how we can start, stop, launch training, stop training. All this information or other action will train using the API. The second interface or the is the configuration interface. And this interface will help us to deploy different components that we need to deploy in the local orchestrator, and also helps us to deploy the models and deploy the models using, for example, protocols like MQTT or SSH. And we try to add other protocols in order to ensure that our platform is interoperable. The second step is the participant management. In this case, we have the compressor and the installer that help us to deploy the local orchestrator. And the local orchestrator is just a lightweight version of the global orchestrator that we deploy in the edge. And this component will prepare the environment, install the requirements directly without just in demand, without manual intervention. The final step is the global model training. We have many components, train orchestrator that will help us to orchestrate based on the logic that we have, the training, global model training, model aggregation, aggregator. Here we will define how we need to aggregate this model. And finally, data processing. And in this case, we have to define data processing information, how we have to process the data. Okay. So like I said, data processing is for personalized machine learning. We have to process the data. And from the global orchestrator, we can define how to process the data, how to aggregate the models, and how to evaluate different models and personalize it. For example, we define our industry meta-learning parametrics, and we can define it at the level, and the global orchestrator will broadcast all these informations. And the final one is the resource host monitoring and host and models metric visualization. And in this case, we have monitoring agent and Grafana interface to visualize all this information collected from the different API of the local orchestrators. But the most important element is for this architecture is the model aggregator and how we have to aggregate the different models. So for that reason, we start thinking how we can aggregate different model, and we have the choice between different model, and in that we start working and thinking about it. And the one of the solution that we will present here is the stacking. Stacking is an ensemble machine learning approach that help us to combine different models and build a meta learner that will be learned from the prediction of a weak learners. So for that, we start with the base model. So we can choose a combination of models that we want to train locally. For example, here we have 4 types of models. We can choose, for example, random forest, XGBoost, logistic regression, and neural network. And each model will be trained with the raw data collected from the equipment. And this data will be, and once the model are trained, will generate a predictions. These predictions will be used by a meta model in order to build a new model that it knows how to combine all the prediction and choose the best combination of prediction. And this prediction, it will be the final prediction. So from that idea, we start thinking how we can distribute the stacking that we have actually to use it in federated learning. So for that reason, we split the stacking model on two parts. The first part will be the meta model and will be the global part of the model. And this one, it will be the local models trained locally and will be the personalized part for the models. Once this part is trained, so each equipment will duplicate, each equipment will have this architecture or this configuration with the same configuration model. And each participant will train the local models locally. The next step is to once this model is trained, we will send it over the network for our meta model to build the global model. And by the end, we will combine the 2 parts, the global model part with the local model parts. So to take a view a little bit, so we can imagine in this case, we have different participants, we have n participants. So each participant will train the model locally using the trained data. And thanks to local orchestrator, because the local orchestrator separates a different participant data, will train, for example, in this case, if we have M equipment, we will train 4 by M models. For each equipment, we will train 4 models. And the local orchestrator will orchestrate the training and the aggregation of the preparation of different predictions. Once all the model or participant finish training the models and generate the prediction, this prediction will be sent to the server. The server will aggregate these models and build the meta model or the global model part, and it will be sent to the cloud or to the local broadcast to the local orchestrator, and the local orchestrator directly will combine the local part with the global part in order to build our model, that is this part plus this part. And this is the model that we will use for the prediction. So what is the most important in this approach? This is a one-shot federated learning. That means that we have just 1 round. We need to train just once to have the good model or to have the global model and the local model. The second one is the local model. we can see that we have dealing with the challenge of data heterogeneity because we have a specified part for that is trained locally and directly with the raw data. So that means that each one knows exactly the data, her data, the local data, and what type of data, and the statistical behavior. We keep the statistical behavior locally, and we know that is the context and the information coming from each client locally. And finally, it's configurable because we can choose any combination of model, depends of our needs. We can use it, we can combine it, and we will have a good model that is trained and adapted to our use cases. So in order to, before starting talking about the configuration or the evaluation of this FEDStack, I want to give you a quick view about the full process of deployment of interaction between the global orchestrator and the local orchestrator. In this case, we can imagine that we have two conveyor or two objects that will be managed by this gateway, and this gateway which will be managed by this server. And we have a REST clients in this part. So if we want a real scenario, we can duplicate this use case 1,000 or 100 of times, and it will be the same everywhere. So the first thing to do is to deploy our local orchestrator. So we have two approach, MQTT approach or a SSS approach. If we want an MQTT approach, we have to deploy our MQTT clients at the edge in order to retrieve the last version of the local orchestrator from the broker and to deploy it directly on the local orchestrator based on many steps that is defined in the client's orchestrator. If not, we have to send, if we want to use SSH approach, we have to define the edge name and unique name, the IP address, password, the port, and the SSH port, the HTTP port, where we now have to start our API, local orchestrator API, and the SSH key in case, or SSH password if we use it, and username. And once all the information are added, sent to the server using the REST client, we can deploy multiple local orchestrator at the time, the parallel deployment. So once this information sent to the server will deploy directly this information, send it to the gateway, prepare the environment, and try to start to deploy correctly the local orchestrator. Once the local orchestrator added or installed, we will add it, register it to our database, and we will monitor directly this local orchestrator, the state, if up, down, connectivity, resources, all the information. The second step is the data generator configuration. So to install, once we have the local orchestrator, we have to register our equipment at the gateway. And in this time, we have to add a category. If we have, for example, for our use case, we have short, long conveyors. So to make the difference between our conveyors or characteristic of the conveyors, we add a category type word, it's a string word, participant name is the idea, and the path data, and where we have to store the data. We will start locally or in a database of how we can store the data in order to use it when we want to train locally the models. And finally is the training. It's the training. Once all this information are there, once all the architecture is deployed, we can start training FEDStack algorithms. And it's good is you have just to send to the global orchestrator the requirements and a descriptor with a JSON, and all the works will be done by the gateway and by the local orchestrator and the global orchestrator, because the local orchestrator will directly instantiate the model, install the requirement if necessary, and train locally the different models. This is right now we have just by the end we will have something like this, an interface web where we have resources, we have communication resources, for example, resources and real-time resources. We have HTTP logs for each local orchestrator. We have a direct access for the local orchestrators. We have also the last global model trained. And here we have the local orchestrator informations and the local info and the model informations. And here we can see the impact of how the model of dioxide carbon use to train the model, and how much energy we use to train our models. And here we collect many, depends of the type of model, we can collect a lot of information about the models and about the data. And finally, each local orchestrator or global orchestrator, we can use directly the API to retrieve the data prediction or directly from the global orchestrator. So the last thing is how we have to evaluate the FEDStack algorithm. This is an important thing. So to evaluate it, we will use a real use case, that is conveyor use case. Because in many, for example, if we take the example of airport, if our belt conveyor don't work, we cannot get our luggage. So it's important to monitor this systems. And also it's a complicated and a complex system, because we have a lot of things. And we have, for example, a combined belt or conveyor belt. We have a composite with 2 or 3 conveyor belts and represent one conveyor belt. So it's an important thing to monitor and to detect anomalies in this type of systems before the breakdown or the chaotic breakdown for many companies. And we work together with a staff company that is specialized in conveyor belt to build a new solution for monitoring. So we have to insert the monitor. For that, we have to insert our sensors and define a new approach for each conveyor and for each use case. And we have a different conveyor in different airports over the world. For example, we have Lyon, Zagreb, we have Mexico, and we have a lot of airports. And this is one of the use case that we work on in the company Carl Berger-Lovro to define a new approach for predictive maintenance. So in this problem, today we will try to talk about one of the main problems, that is defining where our conveyor will operate in on load and no load moments and periods, because this is very important in predictive maintenance, because we can estimate how much this conveyor will use it for per day, for example, and can help us to estimate the lifetime of this conveyor. And the estimation of lifetime is important because we have another models that can use this information to detect other information like anomalies, or when we have to maintain this conveyor, or add change a component or something like this. To do that, we deploy many sensors in this conveyors, and when we try to collect the maximum information that we can, all the information that we can, but not just that, we can also extract some information for labelizing have the labels of any moment of the conveyor. And for that, for example, we have the speed and the intensity information, and we can, from this information, extract other information like the existence of the luggage, or if the running stage, or other way, if is on load or not on load. So the study of speed and intensity can help us to detect a lot of information using all the monitoring interface that we have. So in order to study a little bit to create a real scenario, what we do is that we have many conveyors, and each conveyor will generate the data, and we will use a Raspberry Pi in order to select the data. It's a modest Raspberry Pi, 1 gigabyte. This is the most important, because in the real time, this is what we have in the industrial Internet of Things. We have a CPU of 1.2, and we have a RAM with 1 gigaoctet. So it's not important. It's not a good Raspberry Pi, but we have the challenge to see if FEDStack will give us a good results in this type of environment. And also we try to study the virtualized part. That means that if our container, if we can try to find a virtual gateway, if we can use a virtual gateway in order to build, for example, Docker container as a gateway to send the data instead of using SPDPs. And here we can manage, for example, the resources easily, scale the resources easily without buying a new Raspberry Pi or a PSP. And also, I put my computer, a modest computer, for to train to agree as a global orchestrator in order to build and aggregate our models. So to do the main objective was to on-demand OL deployment, local orchestrator deployment. So we try to deploy the local orchestrator in different gateways, and also to test the efficiency of global orchestrator comparing to the actual model that we use. So because we have many models and we have a big problem for managing this model. In this case, we will try to find out how the local orchestrator can help us to manage these models. And also the dynamic integration of the global model and the local models. That means that if we send the global model, if we train locally the model and send the global model, our local orchestrator will manage this integration between these two parts of the models. So to do that, we have a FEDStack configuration. That's which they say this important part is the configuration. So studying our conveyors, we can observe easily that we have 100 of conveyors use random forest as a model, and others use XGBoost as a model, and it will be complicated to manage it. So we decide to use the random forest and the XGBoost models as a local models, and also we can use at the second level a logistic regression as a meta model or a naive Bayes models, and we can when we try to add new layers. So a meta model composed of multi layers. So in this case, we try to add another layers in for our naive Bayes. Finally, we have the evaluation approaches. For one, the recall approach, the recall metrics is to define if our model is correctly predict the onload periods, because it was the important part for us, the onload periods. And the second one, the overestimation, how our model predicts, for example, overestimate the load period in the predictions. So this is the evaluation. It's a quick evaluation of our models. So we can compare our models with two others. Says the local case, like I said, each conveyor will train the model using the best model, XGBoost or random forest, and the local data. And also the combined approach. In this case, we combine all the data as one data set and we'll train our models. So with the combined approach, just to say that a good model is a model that maximizes the local recall and minimize the overestimation. So in this case, we can see that combined model, we have an important recall, the blue one, we have an important recall on all the category of conveyors. But we can see easily that the overestimation is important. And that means it's not a good model because overestimate the load period. And that means that we cannot estimate the lifetime of, correctly the lifetime of our conveyors, because we can see that instead of 1 hour of operating a load with load, we see 5 hours of load, and it's not correct, and we cannot estimate this period. The second, for that, we can see that a combined approach is not a good approach for us. The second one is the FEDStack based on logistic regression. That means we're just using a logistic regression in order to combine the predictions. We can see that we have the same results as training the model with the local model or the best model that we use locally and with the local data. But what is important is using naive Bayes as a meta model. We can see easily that naive Bayes maximize the green one. We have a good performance for the recall, and also we have an overestimation tends to 0, and this is the most important part. And we can say that naive Bayes is less influenced by the heterogeneity of the data, and this is what we try to find. The last one, or the last slide, is about the resource consumption. So like I said, it's just 1 gigaoctet of training of gigabyte of RAM and modest CPU frequency. So in this case, we can see that before training is the red fuzz, the conception of the local orchestrator. Here we have already deployed the orchestrator, but I want to mention that we have also have also another script for data collection and data aggregation executed with the same thing. But we can see that the CPU consumption is not exceed 10% and 25% for the RAM consumption. Using launching the training, so we use the 4 cores of our CPU, and also we have 80% of the RAM. Why? Because at this moment we have to install the dependency for the models before starting training the models, and also we have to keep in mind that 1 gigaoctet or 1 gigabyte train each model sequentially. So that means that we train the model, each model, and with a big model that is random forest, and XGBoost is a trees model, and is very, very complex, very heavy models that we use in this SPDP. But if we do a second training, that means we have already the dependencies installed. We can see that we have just 60%, 6% of RAM that we use, but the CPU we use the 4 cores, and this is important because if we we replace the Raspberry Pi with the important Raspberry Pi, for example, 4 gigabyte of RAM and a high frequency of CPU, we can get a model, or can have we can train a complicated model with a complicated configuration of FEDStack, configuration of FEDStack. So to conclude, in this presentation, we talked about Internet of Things adaptation, federated learning adaptation for Internet of Things architecture. It's just the beginning of this framework. We're just working. We try to deploy this framework in a real environment in order to test a lot of things, adding new functionality, adding new algorithms like Fed average or asynchronized approaches, and also adding adding the aspects of ML loops, managing, versioning the model, and we already have a version, but it's not developed. Also, we try to add a new traditional machine learning in this framework, and also just we have the option to choose if we have to use federated learning or traditional machine learning. And the most important is the global orchestrator communication. We have to we can to deploy many global orchestrator and to ensure the communication between different global orchestrators. So this is what we are working on now. And finally, is how I said, a FEDStack is the basic algorithm that we use. We are implemented other algorithms based using the vote or other information about the aggregation and adding context aggregation. And we are working also about the selection, because if we have thousands of participants, we have to select just 100 in order to minimize the time of training and evaluation. And all these things is the common work in this framework. For more information, I will share with you these papers. And the first one is describe the approach and the architecture. And the second one is a demonstration paper. And also I share with you a video that 1 hour where we can find how we use the local orchestrator, the global orchestrator, and different possible problem that you will face in the deployment. And that's all. If you have any question.
Yeah, so what I understand that you are training your models locally, right? And the data that you are generating for the training is real time, right? And you're having supervised learning because you mentioned random forest and all those algorithms. So since the data is generating real time, how you are doing the labeling of the generating data for the supervised learning? That's the thing I would like to understand.
Like I said, so like I said here, so we try to implement locally. So I will, sorry. And this is what we add thanks to the global and the local orchestrator. So the main approach in order to labeling the data, so we have to define how to prepare the data and to train the data and extract this information. And this is the main part, like I mentioned here, personalized data processing. So if you have, for example, a logic that you want to implement, our local orchestrator expose an interface, a Python interface, where you have just to define some function, how to train this data, and how to extract this data, and how to store the data. So in this case, you have just to create this script, Python script or Python class, and using the global orchestrator API and send it to different local orchestrator. And the local orchestrator, once receive this information, will train or prepare the data like in the cloud exactly. And also for the evaluation is the same thing. If you have a logic to evaluate your model, you have just to add this logic as a Python script and send it over the global orchestrator, and it will be directly added, directly evaluated with the same approach that you program here. And also it will be directly added to the interface, Grafana interface, that you will see your information directly from the API, because the local orchestrator expose interfaces to retrieve evaluation metrics, to retrieve the local data, installed data if you want to store it in the database, and just he prepare and local orchestrator prepare and store correctly the data.
And have you considered something like reinforcement learning or a feedback to the local models from the global one? So is it something that you worked on, and does it like improve accuracy or something?
So to be honest, no, we didn't start working on that because we try to focus on federated learning and different approach of federated learning. So right here we have just a horizontal federated learning approach, and we try to implement other approaches, other algorithms to evaluate, because our global orchestrator now manage a direct with just one task, not multi-task. We are developing a new management, tasking management. So we try to implement that for just federated learning and exactly for supervised machine learning, to be honest. Just because the most important is to provide federated learning interface to use it for the clients.
I have one final question. So nowadays, networks are being built or imagined with in-network processing. So how would you take advantage of these type of capabilities in this work? So that yeah, so assuming that you have networks that have in-network processing, so you can process the data as it flows through a network. Do you think, how would you adapt your approach, or would it be useful in your case? So you have the cloud, right?
I have all the things at deployed.
Yeah, but you had the cloud in one of your. So imagine you can do some extra processing in that cloud in the middle. Okay, well, we can take it offline then. Okay, well, thank you so much. Oh, we have one question online. Go.
How do we aggregate local models? So let me just, hold on. Hold on. Okay, how do you aggregate local models on the server? Random forest, XG boost, SVM trained weights. No, there's more to it. There's more. I agree. But we don't want to.
Yeah. How do you aggregate local models on the server? Random forest and XGBoost as SVM trained weights are sent to the server. How do you aggregate them into a global model? They are very different architectures. Do you aggregate each architecture separately on the server? How do you deal with poor performance of a local model? Do you filter out any model which has large uncertainty when aggregated at server?
So this is the idea of stacking, because when we're talking about different model, we have a big problem that, for example, neural network, we can use directly the weights. But in this case, we are not aggregating the models, but the predictions of the models that we will use. So in this case, instead of sending the parameters of the models, because we cannot, for example, for random forest, as I said, it's very difficult to combine multi-trees to build just one model. For that reason, we try to find a way to share the data, or to share information and or a vision of one of the models to the other models. And the only solution was to use the prediction, because the prediction describe how this model use this, how this model use the data. And in this case, the main approach, the main step is to we send only the predictions of this model and not the model. So once this prediction sent, we will use this prediction to build a new model, to train a new model that will say, okay, if we have random forest and we have XGBoost and we try to find the weight of each model. For example, the uncertainty weight. For example, we can see that model 4 has, for example, uncertainty of 60%, and others we can share the uncertainty if in the other case. So this is what we try to build with the meta model, and not and the model that will give the weight for each model based on the global view of different prediction coming from the different local orchestrator, and give us a good prediction, give us a good weight for each model that we will be use it in each model, local model. And like I said, the most important is that we have the local vision of our models plus the global vision of our meta models.